Hello, everybody. Welcome in the 3 now. You're going to listen to the presentation Frozen Cache. Maybe some of you have seen 2 years ago Joseph Applebaum presenting the cold boot attack at this conference. And today, which made your encrypted laptops more insecure or less secure than you hoped. And today you might see a remedy, which is presented by our speaker, Jürgen Pabel, and I ask you to welcome him.
Well, thank you for being here. I know I have a tough competition with hacker. I think I'll be fairly quick, so if you want to go over and okay. So I think we'll probably be through in a little bit over half an hour. And if you have questions, we've got plenty of time for that. So, I work as a security consultant, and I have a blog from work which has lots of different topics that I write about, not fairly frequently, but every now and then. And also, I'm going to start my personal blog, whenever there's time. So, first, I'm going to talk a little bit about what the cold boot attacks are, just to refresh your memory. Then I'm going to talk about what the frozen cache approach is, what it does, what it doesn't do. I'm going to give you a demo, which is going to be really impressive because you're going to see a really slow computer. And then there will be little messy details, which I'm going to skip over in the beginning just to get the point across. And then there's time for questions. So the cold boot attacks, they discovered that when you turn off a computer, that your memory doesn't go blank immediately, but rather the data is kept for seconds or even minutes if you cool it down. And in the aftermath of this research, they discovered that there was a paper from IBM which had also discovered the same fact a couple of years ago. But nonetheless, this was the first research. Okay, so that was the research that tied the combination from accessing RAM contents to forming an attack that impacts the security of full disk encryption software. Okay, so now I have 3 mics and so that was 2 years ago here, and also 2 years ago I watched a presentation by Peter Stooch who talked about the core boot, which is a Linux implementation for BIOS replacement. And he mentioned something about the initialization of hardware, where they had problems initializing the memory controller, and that this code is very hardware dependent and needs to be adapted for every single controller, and that was a huge effort to custom create code, assembly code for every single make and model out there. So they were looking for something to make it easier on them. And what they then found was this cache as RAM mode, as it's sort of known on AMD, and known as no-fill mode on Intel CPUs, which allows you to use the cache just as you would usually, but in this mode, the cache doesn't go back into memory. So what they were then able to do is implement their programs, their initialization routines using the cache, so they had a lot more room to implement their logic to initialize the memory controller, and had a lot less worries to implement this. So the idea was then to take this mode and apply it to the as a solution to the cold boot problem, and to essentially not keep the cryptographic data in memory anymore, but to move it on the chip on the CPU, so that if you extracted the RAM, you don't get the cryptographic keys. and extracting the contents from the cache isn't that easy because there's no real interface that you can ask a CPU to, get out the data. And even if you were able to do that, once you lose power to the CPU and you reapply power to it, the initialization of the CPU will clear the cache internally, something that memory RAM doesn't do itself. So, like I said, we're going to skip over some details, and I want you to think about caching as a sort of two-task thing. One is loading data into the cache. Usually it will be something where it will be fetched from memory into the cache, and the second part is then getting the memory, the contents from the cache to the RAM. And for the purpose of this talk, it's most easiest if you think about it as two different tasks that the cache does. And also, we're going to just focus on a single CPU system for now, and even more precisely with a system that only has a single CPU, so no hyper-threading or anything. And I'll get into the details what that means with multi-CPU systems at the end. So, important to know is that CPUs nowadays, they have two levels of cache commonly on the CPU, level 1 cache and level 2 cache. Level 1 cache is extremely fast, usually at clock speed of the CPU, and it's divided usually into an instruction cache and a data cache, whereas the level 2 cache is combined, and any data that's in there could be data that's executed as code or data that's interpreted as data, whereas in the level 1 cache it'll be split up. Okay, is this an execution instruction or is it data? A little side note, in most CPUs, the level 1 cache, the instructions are already decoded. So if you have the assembly, the machine code instruction, in level 1 cache, usually it's already extracted, so the CPU doesn't have to go through the decoding stuff again. But that's just a little tidbit of information on the side. So on x86, and this is mostly for 32 and 64-bit modes the same, you have a control register, 00, which has a couple of bits that indicate the cache operating mode. The one flag is CD cache disable. When you activate this bit, it's essentially the part that prevents data from being loaded into the cache. Whereas the other bit, not write through, is more or less a bit that manages how data will then be pushed out of the cache back into RAM. That's not entirely correct, but let's leave it at that for now. There's also other mechanisms on the platform that can manage how caching behaves on the system. And the first one are the memory type range registers, and they are used to set up specific memory regions for things like graphic card memory, so that any changes to memory regions that are then represented through the graphic card, that those don't get cached, so you get the immediate update on the display. And then there's the page attribute table, which allows for individual pages to be marked as cacheable or non-cacheable. An interesting differentiation is that MTR acts on physical address ranges. So this is really the address that essentially gets sent down to the memory controller to indicate the specific cell that holds that data. Whereas the PAT operates on the linear address ranges, which is practical for operating systems to indicate certain ranges that the operating system deems cache-worthy. And then there's different types of memory with respect to cacheability. And these range from entirely uncacheable, meaning any changes to it will immediately get propagated down to memory, to something like fully cacheable in terms of it can be held as long as possible in the cache, and whenever there's a need to push it out into RAM, it'll be done. So when you want to activate the no-fill mode, all you have to do essentially is flip 2 bits, the cache disable and the not write-through bit, and we have the assembly instructions up here. From what I said in the beginning, activating the cache disable bit prevents the data from being pulled into the cache, whereas the not write-through bit prevents it from being pushed out to the memory again. Turns out this not write-through bit is not really supported anymore. So essentially it comes down to a single bit, the cache disable bit, and the various combinations that you can have with 2 bits, they are documented in the Intel's software development manual. And like I said, the setting of both bits is no longer supported. I think it was Pentium 3 or 4 when that was discontinued. So when you actually turn on a CPU nowadays, when it powers up, the no-fill mode is what the CPU will operate in until the mode of operation is changed by the software. And there are lots of different minor aspects that vary across CPU models. So the basic behavior in terms of how data remains in the cache or gets evicted, written back to memory, are more or less the same. But side effects could be something like when I have this no-fill mode activated and want to know about caching statistics. How much data has the cache held, how much hits have been done to the cache, or how many misses have occurred. That varies a lot depending on what specific CPU you have. So just starting from that, we'll get to it a little bit later, but that turns out to be a little difficult to handle in a generic way to assure that the initial goal, keeping data in the cache, is actually accomplished or not. So it makes it harder to verify. So when you have the frozen cache mode, what you want to do is you want to switch from normal operation in terms of your system is up and running into frozen cache mode, where all your sensitive data is pulled into the cache and removed from memory. So what you do is you take that data, load it into a CPU register, then overwrite the data in memory, make sure that that write actually gets sent down to the memory so that data is no longer present in memory, and then you freeze the CPU and then write the data into the CPU cache so that they now exist there. And for as long as the CPU cache doesn't decide to then flush this data back out into memory, then you don't have the actual values in memory. So what's important, of course, to this mode is that you really can rely on these attributes. You don't want to activate this mode and then turns out, hey, my data does end up in memory anyhow. So the first part is I need to configure the initialization so that data is altogether in cache, and then you have to make sure that it doesn't, incidentally get written back into memory later on. So what data do we need to protect? When we look at full disk encryption, obviously the encryption key, and everybody knows about the AES keys, 128 bits, or bigger, and what's commonly used is the FIPS 197 setup procedure, so to say, which derives a specific encryption and a specific decryption key from the 128-bit that you have initially. And then there's also the key schedule, which are derived keys that are used in the encryption and decryption calculations. And of course, you have intermediary data that occurs when you actually calculate the encryption or decryption. And of course, that needs to be protected as well, because else someone could use that data to run cryptographic attacks on these bits that they find there. So when you initialize it, when you activate the frozen cache mode, you have to consider cache pollution, because when you run the code that initializes it, this is code that can be, or that will be present in the cache, that will be present in the level 1 cache, in the instruction cache, but definitely in the level 2 cache. So this code itself needs to be considered when activating frozen cache mode, and also the pointers to the cryptographic data itself need to be considered. So you have the data you want to protect, the data that points to the data that you want to protect, and the code that actually does protect the data. And if you have questions, just raise your hand and anytime. We have a question right there.
I'm not sure about the PC architecture, but I know from embedded PowerPC processors that there are special commands for the memory management unit and for the cache controller, that you can say, I, for example, reduce the cache size and I grab a slice of the cache of maybe 128 kilobytes or something, depending on the architecture, that I reserve to be a special RAM memory. And this is also, it is possible to address this memory like normal memory. And so you don't have to do this fancy stuff. So if you, for example, have some function pointers just to put some values inside, and then you have to fight against interrupts that could destroy your cache because some evil stuff goes through the cache because there was the DMA stuff, and you have a poisoned cache, and then you have some text that the cache is invalidated, and some routines is destroying your keys and stuff like that. Because it would be very evil to have this as in a normal cache. You would want to disable this section of cache, and you don't want to have this controlled by the cache controller. How do you do this?
Okay, so first off, the x86 architecture doesn't allow you to do that. It's really very basic in terms of what it provides with caching, how you control the cache. Essentially, the no-fill mode guarantees that any data that's in the cache right there will remain in the cache in terms of it won't be evicted and replaced with other data. What it doesn't guarantee is that the data that's in the cache won't, for various reasons, be then written back out into memory. So yes, it would be nice to have more control on how the cache behaves, but it just isn't implemented on x86. So that's one of the aspects is, okay, with this no-fill mode, you know that the data is there. What you don't know is, has it been written back into memory yet? And that's something I'll get to at the end in determining, okay, has it been written back or not? So, does that answer your question, sort of? I know it wasn't really a question, but was that the information you wanted? I'll repeat.
So roughly, but it proves that the x86 is an evil architecture that is full of flaws, and it's not worth to do serious stuff with it. Because if you cannot disable a cache controller, and if you cannot say I want to use half of the cache controller, this is a rotten architecture.
Yeah, but it's hard to find good laptops that have a docking port, that have reasonable power, that have all the nice interfaces that you want, and are, not custom engineered so that you can afford them.
There are some other processors like Spark that are also fine. So the point is if you have a rotten cache controller that you cannot, or can you disable the cache controller at all, or it would be fine to put the AES core also inside the cache, so the AES with the keys is doing its stuff and is looking there and is sitting there and has some fun because it's executed quite fast and the keys are in a safe harbor, and so it would be perfect to do it like this.
It would, just not on x86.
So it is rotten.
Okay, so one of the aspects, like I said, is you have to protect various data, and you have to consider the initialization function and make sure that everything will actually fit in your cache. So one component of the frozen cache is a level 2 cache emulator, which verifies that the data you want to put into the cache will actually fit into the cache when considering various constraints that caches have. Just because you have a cache that's 2 megabyte doesn't mean that you could really effectively put 2 megabyte of data in it because of associativity and other issues that might reduce the effective size that you can put into it. So therefore there's an emulator that verifies that you want to add some data to it, and it checks, okay, will this work or will this not work? And of course the level 2 cache emulator itself is also part of the data that needs to be put into the cache itself. So all this is implemented in the enable car function, which caches RAM is what that is supposed to mean. And obviously this function, you need to know what you program, how that ends up as a compiled binary. So first off, it uses specific directives in C, like the register directive, so that your variables that you have are kept as a register and not used in RAM itself, which could then impact your calculation for the cache usage. And of course, it's used compiled with without optimization. So what you tell it to do is hopefully what it will compile. Interrupts will be disabled in this initialization routine, so you don't have any other things that will go on that would interrupt. There. Repeat, please. Later, messy stuff. So everything is inline, so there are no calls, so that okay, I have a chunk of code that will execute, and this is all in one block that I could then consider for the calculation of the cache layout. And there's no stack or heap access, because that would also impact the data in the cache. And of course, the only exception for that is the target set, that what you want to be in the cache. And then there's a performance check that measures how long it takes to access the data. And if you measure a difference before the setup and after the setup, then you have a fairly good assurance that your data is now in cache, because when you have to pull it from RAM, it'll take a lot longer. So the problem, like I said, is it's slow. It's really slow, and I'll show you how slow it is. So what you need, one of the things that still needs a lot of work is using the so far unused space in the cache to add performance relevant code into the cache, so that it helps improve the performance. And an example for that could be the interrupt service routines, so that you don't have slow timer interrupts, for example. Obviously, it's a good thing only to activate this when it's really necessary, and necessary from a security standpoint. If you have your laptop and your screen isn't locked, then who cares about the cold boot attacks? I have access to your data anyhow. And standby could be another part where it could be interesting, but I haven't looked into that too much, so I don't know if really standby is something where this could work or not. Questions? Okay. So I'm demoing this on my presentation laptop. I'm fairly sure it works, but we'll see. So activation, I'll do it one-handed. So activation of frozen cache mode is controlled using a proc file entry. And the proc file entry is proc frozen cache. And the primary purpose for using the proc file system instead of the system, because it was easier to implement. So what I'm going to do first is I'm going to deactivate it, and I mean it's deactivated right now, but I deactivate it because I can then, after I activate it, disable it again using just 2 times the up key and the enter key. So there. Okay, so what's really interesting, okay, so I hit the up button, that was fairly quick. Hit it again. Okay. There you go. What's interesting is that the graphical subsystem or the graphics accelerations aren't impacted that much because the graphic card does that. So if I were to minimize the window and then switch back to it, all the nice GUI stuff works perfectly, but anything the CPU does, like switching a task, etc., it takes forever, so I'm not going to do that. But you know, the little whatever disappearing effects, they work nice. So I've already hit enter on the deactivation again. And this is without much optimization. So right now it's only the target set of cells that's in the cache. So the goal would be here to get the target set, to extend it to include the screen lock, for example, so that you can type in your password and not have to wait forever for it to process your inputs. So I've got some frozencache. I've got some debug messages that are outputted, and the first couple things, they happen at boot time because the kernel module, frozencache as a kernel module, is loaded as part of the initram FS initialization. And right here we have the first chunk, which is 1024 byte. That's actually the initialization function, so the enable caches RAM function. The next part, 256 byte, is the array of pointers to the target data, plus an array that holds the length of data to be protected. And then the next 4 lines, there are actually 32 bytes each. Those are actual cryptographic keys that are used. There are 4 because there's a copy in the mcrypt that needs to be protected. Then there's a copy inside the cryptographic implementation, in this case AES, and I think I have 4 because I have another partition that's mounted, but I'm not really sure right now. No, wait. Those are actually just 2 because there's add to cache as RAM, which is 32 byte, and then the add to dcache, which is the emulator. So this is actually just the key ones in dmcrypt and ones in the AES cryptographic part that are shown. So that worked out. And a lot of the messages you saw there, they're not really all that useful right now because it's work in progress, and really work in progress. It does work, but it's, you know, not completed. We have another question.
I have an idea, but I'm not sure if this works because it's unclean. What about so in the cache controller there always is there are tags that say that this memory address is dirty. So because maybe you have had in DMA. So the thing is, what about setting on purpose some areas in the cache dirty and use the dirty areas in the cache? So the cache controller won't touch them because they are dirty, and you can do what you want with them.
The way I understood your question, it doesn't make sense, so I probably didn't understand it correctly. You said you want to mark data in the cache as dirty in terms of different from what's in memory?
Yes. Yes, and that's right. Yes. Yeah.
That's the state, actually. That is the state. So in no-fill mode, the data is actually different in cache than it is in RAM. In RAM, the area with the cryptographic keys are all zeroed out, whereas the representation in the cache is actually the key data that's in there.
The idea was to use the cache as normal, but say on purpose with some evil tricks that this some area in the cache is always dirty because you mark them as dirty, and so they are not used by the cache controller.
Still not.
But we have to think about it. It's just an idea, but you have to find in the data sheets if it's possible to do this.
Okay, why don't we have a talk later on? Because I think you know a lot of aspects that I might not have discovered yet. So let's talk afterwards. And at the end, I'll have a few aspects that are in addition to DMA that might impact the effectiveness. So Frozen Cache is kernel module. It has actually a copy of the encrypt. A copy because the encrypt, there need to be a couple of hooks that actually invoke Frozen Cache, like telling Frozen Cache, okay, the cryptographic key is actually right in this memory location. And I really don't like the fact that the encrypt is a copy inside this module, but I didn't find a good way to sort of grab into another kernel module and get the data out from there, or to add a hook there without binary instrumentation, and I just didn't want to do that. So it was much easier to copy it, add a few lines, and be good. So when you actually move the data into the cache, you do it one cache line at a time. A cache line is essentially the single entity that the cache operates on, and usually it's not a byte, but it's commonly nowadays 64 bytes. And so when you have a like the 1024 byte area, that gets pulled into the cache 64 byte at a time. So it's the bootstrap code, the pointer array, and the cryptographic data, the three pieces. And the activation of Frozen Cache mode, I have a little Python script that I tested out to make sure it does work, but it's not usable just like the rest of the system right now. So the idea is to have a dbus listener that detects, okay, screen lock is on, let's go into Frozen Cache mode. So cryptographic data is scattered in RAM in different places. Like I said, one is managed by the mcrypt, others by the actual cryptographic implementation. The intermediary data is on the stack usually by the implementations, just because it's variables that are used in the calculation. So like I said, the mcrypt has added calls to hooks, which then add this data to the cache, and that's easy because it's just a call. Whereas the intermediary data that's in the calculation routines, that if that's on the stack, you need to figure out, okay, so which memory page is this stack frame on at that time, and then load that into memory also, and that's also work that still needs to be done, and that really will require additional calls to the implementation of the encryption routines. So same question, where are my bits? Different aspects with respect to, are they in the cache, are they in memory, are they both? I mean, are they not in the cache anymore? And because the x86 caching system is so trivial, so simple. I mean, you can control what you want to cache, but you can't determine what's in the cache and all that. There's the risk that any instruction that operates in the system that has required privileges that can initiate an explicit cache flushing, indicating to the CPU that the cache content should be written back to memory. Obviously, that's a problem, and one way to determine this is to access the CPU cache statistics, and that's a special register that the CPUs provide, where you can get the information, okay, how many cache flushes have occurred since the last time these counters have been reset, or just take a different, the difference from the last time you measured these. Other ideas to make sure that your data doesn't get written back into memory could be to use non-existent physical addresses. So you write your data to a different memory location that if the cache tries to then push it back into memory, it would result in a CPU exception. And that's something that I've played with a little bit, but I just couldn't get my specific CPU to work with that. I'm fairly certain that different CPU models will behave different. So there might be models that can be tricked into that. So you have the assurance that your data never gets back out into RAM. Another idea would be to use device-backed physical addresses. So maybe your data doesn't end in your RAM stick, but rather maybe in a dedicated graphic card or any other device-backed addresses. Whether that's feasible in terms of not impacting the behavior of that device or anything is something that I haven't looked into. So, messy details. I already mentioned cache associativity. With the caches, they have a certain mapping, so you can't fill out just 2 megabytes of data into the cache for any reason, but you have to consider how is the mapping that the specific cache has, so that you don't overwrite an entry that the cache would then say, okay, I would have to push it out, or I just don't have a free slot for it. Cache hierarchy is an issue. Usually you have a first and second level cache. Now it's the modern server CPUs, they have a third level cache. Other motherboards, for example, have a third level cache that they provide on the board. And hyper-thread and multi-core systems, they are sort of good because you could then put one CPU into this mode and get still full performance from the others, as long as they don't touch that address that you're keeping in the cache of one CPU. If another CPU were to touch that data, they would issue a snoop instruction to the CPU, asking, okay, so who has this data? Is there anyone who has it? And is that data maybe even modified from what's in memory? So one important aspect would be then to bind the kcrypt-d kernel thread onto that CPU that's actually in frozen cache mode to make sure that only this thread accesses this data, and if it's bound to the CPU that's in this mode, there shouldn't be any problem. Back to your notes from the beginning, system management is something that I haven't really thought about in terms of what that might do to CPU caches. I mean, it's not anything that you would expect for your regular laptop to impact you when you're working, but it's something that needs to be looked at and determined how can this be handled, or is that something that, you know, if system management mode is detected, then maybe a pop-up box or just any kind of warning indicating that the correctness isn't there anymore. And also CPUs that provide CPU virtualization, like the VT, they also have impacts on the cache. So that's also an area for more research. And something really nasty is speculative prefetching. That's a CPU internal mechanism. Was there a question? Oh, okay. And that's something that you really don't have any control over. So other than looking at the statistics, there's no way to determine whether prefetching actually has impacted the operations. So there's a lot more work to do, and I'm going to get to it, but it'll take a while. So this has been the talk on the current state, which is sort of the proof of concept, but not the complete solution. So I think I'll release the source code once it's sort of completed, not in terms of a perfect solution, but once it's so that others will be able to extend on it, understand it, look at it. My goal would be for this to be within the next 3 months. So now, questions. Thank you. Although I know you have more questions. Are there any other questions? Maybe that. Okay, now you have the mic, so go ahead.
Okay, so I just had another idea. Normally computers have graphics processors, and graphics processors could also have caches. And these graphics processors are having normally a very dull life, making a 2D desktop and sitting around and waiting for some work to do. And so I think it would be possible to take the cache of these graphic processors, because they also have the tendency to get hot, and so they fight against being cooled down with some cooling agents.
That's what. That's one example of the device-backed memory address ranges. With most laptops, which that would be the perfect deployment scenario for this, you usually have integrated graphic chipsets that you don't get any benefit because they use the memory for their backing. So if you have a dedicated memory card, yes, that would be a reasonable example, and it's something where I think it could be done without impacting the operations of that device. So, other questions?
Does it work? Yes. Okay, there are 2 questions from the peace missions. The first is, do you have any idea for how to verify that the keys are no longer present in RAM?
So the answer to that would be the cache statistics that are provided by the CPU itself. So you query it, how many cache line flushes did you have, and if the value that comes up is the same as before, then for all you can tell with the CPU, you have to rely on that. The perfect, or so the real answer to that would be, okay, activate the mode, extract it, do a cold boot analysis, and then see if you can find the pieces of data that you are looking for. But how many times do you have to do this to really be sure that you have had maybe that one situation where data can be pushed back out into RAM, even though it isn't documented? So it's something that would have to be an automated test, and I don't think that's really that feasible. So, no, based on the documentation, you could be sure, but yes, there's a gray area. The second question?
Yeah, the second one is, do you really think that the CPU is such a much harder target than RAM, given that in both cases physical access is necessary?
Given the CPU is what?
The CPU is such a much harder target than the RAM.
Yeah, so it's based on the documentation. There's no way to extract the cache contents from the CPU, except maybe indicating a snoop on the pin for the CPU, asking whether any data in the cache is relevant to JTAG on Intel CPUs.
I said that could be possible with JTAG, because there are some fine debuggers from American Arium and other companies that will reveal you also the cache contents, because otherwise you will not know that a evil DMR transfer destroyed your cache contents and stuff like that.
Okay, so I think if I understood this correctly, the idea there would be to use the trace cache from the CPU to detect whether any flush caching has occurred. Is that what the...
Yes, but for example, if I would be an evil person to grab your computer, I could try to freeze it and take JTAG to get the cache content. because I just have to write some small assembler program that I put in via JTAG somewhere to be executed, and then I read your cache and put this data to the JTAG IO transfer cells, and I get the data.
I think that's correct, although I'm not aware how many systems provide a JTAG interface in terms of laptops.
A big computer, every CPU that has some means to be a good CPU has a JTAG, and so
We're talking about x86.
Yes, but I know, and in former times I developed boards, and I know that the Pentium 3, for example, has JTAG, and the better CPUs will definitely have JTAG.
Okay, so yeah, I think that could be an attack vector. If you have a JTAG interface that you can connect to that provides you the access to inject code into the system, yes, I mean, of course, then game over, definitely.
Hello.
Okay.
Okay. To get this crypto problem under control, did you know some hardware that can solve this this error, or how you will know it, with the crypto keys that lies in the memory out of the CPU RAM? Some special.
Right. Any other ideas? So is that your question? I think, just off the top of my head right now, I think there could be plausible to use the if you have a network card that has a crypto accelerator, then maybe that's something that you could employ to do the calculation and even offload the keys into the crypto accelerator on the network card. But I don't think that there are any laptops that provide, a network card that has a crypto accelerator. And whether then, if you do have a system that has that, I don't know if you can actually offload the key onto the network card. I just don't have any experience with that. So yeah, but if there are other ways to sort of complete the cryptographic computation by any other device that provides a much more complex sort of access logic to the memory, to its own memory, like a network card. You pull it out, you initialize it. I would assume that any data in there is erased, although maybe that's not the case. But the essential problem there is that memory itself, you take it out, you put it in somewhere, it doesn't have any self-initialization, so to say. And if you have a memory-capable device that has self-initialization capabilities and prevents you from accessing the memory directly, no? I'll repeat. If you talk loud enough, then I'll repeat it. Very good note. So the note was that even if you have such a device, it really wouldn't protect you, because if you manage to reset the CPU and, for example, start your own operating system on it, then you could then give the instructions to tell whatever component you have to just do the calculations for you, or to maybe give you back the keys. So yes, it would have to be a combination of not being able to extract the keys from the device back. So yeah, probably the network card with the acceleration probably would not be that. It would probably be better, but if that's really the perfect solution, is, I don't know. Yeah, but that's really good idea. Yeah.
Okay, then another question from the peace missions here. So what's the point of keeping just the key data out of RAM when RAM is likely to contain a decrypted working copy of a part or parts of the data anyway?
Correct. So the first answer to this is it would be hard to move all your data that you have in memory into the cache. I mean, you have a PDF open or your email, that just blows the size of your cache. Of course, you could just purge all that data, maybe into encrypted swap, and then reduce that attack surface. But on the other side, it's only the data in RAM that's in RAM at that time. If you have one email open, yes, they could read that one email, they could read 10 emails, but they won't be able to access your archived folders from the last 10 years unless they are present in RAM. As long as they don't have access to the keys, so they wouldn't be able to decrypt the data on the disk. I think there's another question over there.
Right, so this is related. Suppose I would want to provide an operating system service that lets applications specify that some data contains cryptographic keys and should be stored in the cache in some specified situation. Can this be done, in other words, when you don't have control over the addresses and layout of the data? And if so, how much memory can I reasonably store in the cache as a proportion of the cache size, perhaps?
So the question is, given the associativity of the cache, how much data can you actually put into the cache, like in real-world situations? I would have to guess. My guess would be maybe 5%, 10%. So 100 to 200 kilobytes with a 2 megabyte level 2 cache. That could be way off. I don't know. It could be 1%, it could be 50. It's my semi-educated guess.
But you have an inherent problem, and you cannot solve it because you have to store the keys in something that behaves like a RAM, and you have to be able to read the keys. And if the CPU is able to read the keys, then any other setup where you put the CPU or the system to can also read the keys. So the only thing that you can do is having some special hardware device that detects that some evil man is coming and then tries to wipe the data. Or you have a one-time pad that is hidden and you XOR your RAM with this one-time pad that you have hidden somewhere and you wipe this one-time pad or change this one-time pad, for example. Having a linear shift register that moves this one-time pad somehow so that it has another value. But you have to make a special custom hardware to do this.
That would be my view also, yes. Although I wouldn't have thought of that 10 minutes ago.
If there aren't any urgent questions from the audience, I would take one more question from the internet and afterwards close because we have to.
I'll be here,
keep in
so
time.
anyone who has questions, come talk to me, and I'd like to talk to you. So that'll be interesting.
Any urgent questions in the audience? Okay, thanks.
So, so much, yeah, I know, but so much for me being through in 30 minutes.
Okay, the last question is now from Peace Missions. The question was, has he looked anything into Intel Core i5 with IIS acceleration? So, have you looked?
I've read about it. I've not read that much about it to determine whether the new cryptographic acceleration components that are in the CPU allow you to actually move the key into the CPU, or whether the acceleration component will only act on data that's in RAM or in the cache. I don't know. My guess would be that it doesn't provide that capability, and it rather just act on memory, because that sort of fits along the paradigm that the x86 platform does with the SSE and all the other multimedia extensions. They provide more complex operations, but no additional capabilities besides computational computations. So my guess would be no, but that's no more than a guess. So thank you, and go over there or have fun tonight.